Welcome everyone to today's AM Academy webinar, part of our ongoing series that's designed to make cutting-edge materials science and engineering knowledge more accessible. My name is Zara and I'll be your host for this session. And today's talk is titled The Basics of Self-Driving Labs, How Machine Learning Accelerates R&D Workflows. And it's a topic that's becoming increasingly relevant for researchers, engineers, and industry professionals aiming to make smarter, faster decisions in the lab. And I'm very pleased to introduce Dr. Mohammed Jeraal, Director of Engineering here at Accelerated Materials. And Mo is also the lead developer of AMLearn, our in-house AI platform, and he has a strong background in applying automation and machine learning to chemical R&D, working with companies like Pfizer on real-world process optimization. So in this session, he'll walk through why AI is essential for modern R&D, the tools and techniques that power self-driving labs, and how AMLearn fits into this picture. And we'll also go into some real case studies that show how this is applied in practice. We'll also be leaving some time at the end for a Q&A, so feel free to drop your questions into the Q&A box throughout the session, and we'll be sure to get to those. And with that, I'll hand over to Mo to take us through the presentation. Over to you, Mo.
Hi, everyone. Thank you for that introduction, Zara. Thank you all very much for attending. So, as Zara mentioned, today's presentation will be on the basics of self-driving labs and how you can accelerate your chemical R&D processes using a combination of AI and machine learning. So I'll get my slides up. We should be able to get started. So, yep, today's presentation is going to be an introduction to self-driving labs. It's going to be quite a simple introduction, so you don't have to worry if you don't have too much information on automation or statistics. This presentation is not going to require any programming language or go very deep into any of those concepts. It's just an introduction to get you familiar with the concepts. So the presentation will, or the webinar will be roughly split into 3 phases. I'll start off by kind of going through some of the approaches that a lot of you might already be using for chemical process optimization. We'll discuss why they're strong, some ways in which they're limited, and then neatly transition into how AI and machine learning technologies can help to address some of these shortcomings. And then finally, at the end of the presentation, we'll throw some automation in and see how we can really use that to help supercharge our chemical process optimization and really reduce the time and cost needed to do it. Like Zara mentioned, if you have any questions at any point, just feel free to throw them into the chat, and I'll be happy to take them at the end of the presentation. So I know that many of you are going to be process chemists or process engineers, and a lot of you will be familiar with the pitfalls of chemical process development. Modern R&D can be very complex. There are so many variables that we have to control: reagents, concentrations, temperatures, times, pressures, the number of steps, the order in which we do things. And sometimes, even if we just have a handful of variables, if you begin to calculate how many combinations are needed to exhaustively test all of these combinations, the numbers can quickly become astronomical. And I know that for a lot of us, our resources are not infinite. In order to run experiments, to analyze materials, chemicals themselves aren't always affordable. So it's always in our best interests to try to reduce the number of experiments because we simply can't afford to test everything. Another concern, or another issue that's becoming of increasing concern is multiple objectives. So it's no longer just enough to be able to maximize the yields of our processes. With increased competition, regulatory concerns, we often have to consider things outside of our yields and our purities, things like the cost of our reactions, the greenness of our reactions, and all of these objectives can further complicate our chemical optimization processes. So as mentioned, I'll start by taking us through some of the existing processes, some of the existing ways in which you might be optimizing your chemical processes. And the simplest of these is one variable at a time. And it's quite simple. Something I'm sure all of you have done at some point, where you just take all of the variables in your reaction, you hold all of your other variables constant, you take one variable, you vary that, you optimize it with respect to your given objective. And once you've got the optimal value of that one, you keep it constant at that optimal value, and then move on to the next variable and begin to vary that. You then sequentially go through the process until you've optimized all of your variables. It's quite nice. It's very simple. It's easy to run, and it's easy for you to kind of keep track of what's going on in your optimization process. We'll kind of see how it works with a short example. So we're going to look at a hypothetical chemical reaction here that we're trying to optimize for yield. And in order to optimize our yield, we're going to be varying the concentration of one of our reagents and optimizing the temperature of the reaction. And at the start of an optimization, this is how you're going to see the plot. You'll be completely blind, and if you run the optimization, you likely don't have much idea of how the concentration or how the temperature is going to influence the yield. So for the sake of this demonstration here, I'm actually going to show you what the effect of concentration and temperature is on the yield. And you can see how it varies relative to this color scale on the right-hand side. So let's say that you're starting this optimization and you don't see the contour plot in the back. And what you might do is you might decide that you want to vary concentration first. And in order to do so, you might fix your temperature at its medium value, at 50 degrees. And then you'll run a series of experiments at concentrations, 0.2, 0.4, 0.6, 0.8, and 1. And you'll see that of those, the experiment at 0.4 seems to have the best yield. And it's really not bad. We've got a yield of about 50% before we've even optimized our temperature. That's decent. It's nothing to be sniffed at. So now that we know that 0.4 molar is quite good, we can fix our concentration at 0.4 molar and begin varying the temperature. And we conduct some experiments at 10-degree increments. If you want to be more accurate, you can go 5-degree increments. And you can find out that 60 degrees at 0.4 molar gives us the best yield that we've seen so far in this optimization. If we compare it to the color scale, we're roughly at about 70%, which, again, nothing to be sniffed at. It's very good. And if you were to do this optimization blindly without the contour plot in the back, this could be considered a reasonable result. But it's only when you overlay the actual results, we can see that we actually have this very highly yielding area with about 90–95% yield that we completely missed from our process. So I guess this is one of the limitations of one variable at a time, where it's often very difficult to find the true optimum in your system. And the performance of the process is very much dictated by these seemingly arbitrary decisions that we're making at the start of the process. Let's just say by some happenstance, you fixed your concentration at 0.7 at the start and then varied temperature, and you did manage to stumble upon this region. There's every chance that this optimization space was more complex that we're seeing, and there was like an even higher yielding area here that we would have completely missed. So it's very difficult to find the true optimum with this technique. Another thing is efficiency. So we've had to do 9 experiments here to optimize for just 2 variables. And as you increase the number of variables, the number of experiments needed very quickly goes up. Because we're only varying one variable at a time, we don't really get any understanding of how the variables influence each other. One of them is always fixed whilst we're varying the other one. We have no knowledge of the interaction between them. So one way to address this is traditional design of experiments. Now, a lot of you will be familiar with this, and it is a big step up from OVAT, from varying one variable at a time. You can understand so for those of you who are unfamiliar, what we do is we run a cube of experiments. So this point here will be at a low temperature, low time, and a low concentration. This point here will be at a high temperature, still a low time, and a low concentration. And then we just go through the grid systematically. So because we're varying more than one variable at a time with each experiment, we do get some understanding of the interaction effects between them. And it does mean that we can really reach solutions much, much faster than one variable at a time. And so if we just compare to the previous experiment, here we've got 3 variables and we've got 8 experiments. So we're already much faster than the previous experiment where we had 2 variables and 9 experiments. But it does suffer from a lot of the disadvantages that the previous method suffers from, where if we're increasing our number of variables to far beyond this, so we've got 2 to the power of 3 to get 8 experiments here. But once we start introducing 8 or 10 variables, and you're up to 2 to the 10 experiments, suddenly the number of runs goes up drastically. Just like with the previous optimization technique, we can only optimize for one objective at a time. So multi-objective problems are quite difficult to do with these techniques. And finally, with these traditional design of experiments, it is on the user to model the data after they've performed the experimental design. And the experimenter is the onus is on them to select the best model type. Usually it's likely to be a linear model or some kind of polynomial or multivariate model, but it is up to the experimenter to make this decision and have sufficient knowledge on the system to make sure that they're making the correct decision here. So this slide summarizes the limitations of the traditional way of doing things. So yeah, the number of experiments can very quickly get out of control with both optimization techniques. With DOEs, you can do things like partial factorials or de-optimal designs to bring the number of experiments down. But they are still very high compared to other techniques that we're going to discuss in the presentation. Dynamic adaptation. So let's say you have a difficult problem in your DOE, where imagine that this is a larger grid and your highly yielding experiments are only in this region here. You have a large grid of experiments that's going out from here. If you discover that your experiments are only valuable in a small area of the grid, you don't really have any way to adapt your process to focus on the areas which are more promising and avoid wasting time on the areas which are not producing any results. Discrete choices. So with DOEs, this can drastically increase the number of experiments needed to assess all of these choices and the combinations of these discrete choices. And we've already discussed how multiple objectives can be quite difficult to tackle using these problems. Using these techniques. So on the next slide, or in the rest of the presentation, I'll be showing you how we can use AI and machine learning techniques to augment your chemical process optimization. And the thing is that we're not rewriting the rulebook and tearing things up. It's just a case of making some smart choices to improve the way in which you do things. So in this presentation, I'm going to be referring to a very specific way of doing machine learning for chemical process development. And I do want to be clear that it's by no means the only way of introducing AI and machine learning into your development processes. So for instance, if you've got large swathes of historical data, you could use predictive modeling in order to model that data and just give you some experimental conditions to run. If you're earlier on, you're not necessarily optimizing your process, but you're designing your process. You're coming up with a synthetic route to make a particular molecule. One way in which to tackle that could be data mining. Organizations like Elsevier have huge databases with millions of reactions in them. And data mining can help you to pass all of that information to come up with a retrosynthetic pathway through which you can make your materials before you're at the optimization process. For process control, you can use things like autoencoder models for things like fault detection or predictive maintenance. These tools are, I believe, are already being utilized industrially, and you could use those too. So generative models are probably quite hotly contested at the moment, and they do seem to be quite polarizing. People either think that they're the second coming or they're completely overhyped. And I think that the truth is probably somewhere in between. They can definitely have their uses. They're quite good at parsing large amounts of information, large amounts of text, and drawing conclusions and creating summaries from those. One way in which it could be used, for instance, is to come up with novel procedures or novel ways of doing things that we perhaps might not have thought of just by combining things that have been done in the past. But as you can probably guess from the slides that we showed previously, this presentation is going to focus on chemical process optimization. So this is when you have your synthetic route, you have an idea of the steps in your chemical process, and you just want to refine the solvents, the acids, the bases, and the continuous variables needed to get the most from your chemical process. And as we've seen, this is a process that can take weeks, months, years, as in for challenging processes. And all of this time that's taken is not just time, but kind of labor, resources, chemicals, all of which can be greatly reduced through the implementation of machine learning technologies. So the technique that we're going to be discussing in today's presentation is Bayesian optimization. And unlike the previous methods that we've discussed, it's a systematic solution that attempts to find you the best solution for complex problems using minimal experiments. And the key difference between Bayesian optimization and the previous techniques that we mentioned is that it works iteratively. So every time you run an experiment, you give the result back to the system so that it can use that information to tell you where to go next. So it prioritizes the areas that it feels are most promising, so that you're not wasting time and resources on fruitful endeavors, or fruitless endeavors, sorry. The key thing to note is that promising areas doesn't always mean areas of highest yield. So sometimes there might be areas where system has less information or just needs to understand how the inputs are affecting the outputs in that area. And as a result, you might get an experiment pop up in that region. So Bayesian optimization is increasingly becoming more versatile. So in its infancy, it was typically utilized just through a specific type of model known as a Gaussian process model. We're going to come to that later in the presentation, and that has its strengths and its weaknesses. As Bayesian optimization is spreading to incorporate other models, things like neural networks and the boosted decision trees, it's becoming very, very versatile, and it has the ability to handle really quite complex multi-dimensional problems. So in a chemical context, this means multi-step chemical reactions where you're optimizing for discrete variables as well as continuous ones. And I'm not going to go deeply into it in this presentation, but uncertainty is a huge component of Bayesian optimization. This means that whenever a model is giving you a predicted yield or a predicted particle size or a predicted cost for a reaction, it will always give you the uncertainty measurement associated with that. And that uncertainty is used to guide the optimization because it determines where we have information and where we don't have information. And by knowing where we don't have information, then we have some guidance on where we need to search to ensure that we're not locked in a local optimum and that we've scoured the optimization space and we have this true global optimum. So this slide shows the Bayesian optimization cycle. So if you Google Bayesian optimization, you'll likely find countless images that look something a little bit like this one. So the way it works is that you start off with some initial data. Now, this could be data that you already have, or you could perform some initial experiments. I won't be covering it here, but there are recommended ways to collect those initial experiments if you don't already have them, in order to optimize the information that the model can get from that data later in the optimization process. So once you've done your initial experiments and you've calculated the yields or measured the particle sizes, what we then do is we fit a predictive model to that experimental data. Once we have a model, we use that fitted model to basically go through thousands of hypothetical scenarios, and of those, find the best experiment. Once we have the best hypothetical experiment, we physically go and run it. In addition to that, then we will characterize it, measure the yield, measure the particle size, and once we have that information, we'll feed it back into the data set and fit a new model with this updated information. So from this, then the system knows what worked, what didn't work, did it improve the yield, did it not? They can use that information to then go through the cycle again. And this cycle just continues until iteratively you've optimized all of your objectives. So I've tried to stay away from jargon. I know that a lot of machine learning resources online can be quite jargon heavy. So whenever introducing some new terminology, I'll try to explain what it is and not to labor on it too much. So I'll be using the term surrogate model. And if you ever see this term in the literature, it's just a model. It's just a model that you're using in order to represent your chemical process. And an acquisition function is just the decision-making process that you use to select the best experiment from those thousands of predictions. Could be just as simple as randomly selecting one. That is an acquisition function. It's not a very good one, but it is one. Another way to do it would be just to rank all of them in terms of yield, and then taking the experiment with best yield at the top. That is a better acquisition function. And in more complex forms of Bayesian optimization, like the one that we use, there are complex mathematical functions that basically trade off the various objectives together with searching the optimization space. But the key thing to note that all the acquisition function is doing is just making that decision on which experiment is best to perform next. So I'll start off by taking you through the first step of this reaction. Once you performed your initial experiments, what we need to do is model the data. So AMLearn is our software, and I'll take you through some of the ways in which it does surrogate modeling. As I've mentioned before, a surrogate model is just a model. And the reason why we use models is because experiments are expensive. I mentioned this a few times in this webinar. And what the surrogate model allows you to do is to predict the results of thousands of experiments without actually having to perform them. And it could be very simple. I mean, it doesn't have to be something very complex like a neural network. It could just be linear regression. Height and weight. Let's say that you're just crazy about using the seesaw and you just want the optimal seesaw experience. You know that you weigh 73 kilos and you want to find somebody else who also weighs 73 kilos to kind of ride this seesaw with you. But you don't have a pair of scales, you only have a tape measure. So what you do is you, with some consent, measure the heights of various people. And rather than having to do that, the model can tell you, once you found somebody who is 176 centimeters, they will likely have a weight of 73 kilograms and give you this optimal experience on the seesaw. And the process is just as simple with chemical processes. Unfortunately, our chemical processes are rarely that simple. Our reaction pathways are often quite complex, nonlinear relationships. We often have multiple variables, not just one, and they often interact with each other quite complexly. And because of this, we need more powerful models in order to capture this complexity and be able to sufficiently model our reactions for the Bayesian optimization process. So over the next few slides, I'm going to be going through the models that are quite commonly used in Bayesian optimization, the models that are available in AMLearn. So I'll just be giving you a brief introduction to these models. And there are a lot of things to consider when using these models, such as the parameters and how to set them up. In this presentation, this will just be a brief introduction. And if you guys are interested, then in future webinars, I can go into that information in more detail. So the first type of model that is most commonly used for Bayesian optimization is a Gaussian process model. So this is just like the height and weight chart, where we have our variable on the x-axis and its response on the y-axis. And this black line is just the mean curve that shows how the variable changes with respect to the response. Sorry, other way around, how the response changes with respect to the variable. The key thing to note with Gaussian process models is that we don't just fit one function. We actually have a distribution of functions at every variable value. And you can see the red points are experimental points. And as we get more data, we collect more experimental points. That uncertainty basically just collapses down onto itself and gives us more confidence in the predictions that we're making. You can see how Bayesian optimization then can use this in a very powerful way to decide where to search and where we have more confidence in our values. So these mathematical functions are known as kernels. They're very flexible and very nonlinear, which makes them very well suited for kind of complex chemical interactions. One of the downsides of Gaussian process models is that they can slow down when you've got a lot of data points. But the nice thing is that in chemical reaction optimization, a lot of the time we're probably going to have maybe 10 reactions, 20 reactions, 50 reactions, 100. We're never really reaching the areas where that slowdown is going to begin to take effect. But because of this uncertainty, Gaussian process models are very good at searching, and they're quite versatile. So they're quite good with simple processes, moderately complex processes, and it's only when you start going to very extreme processes where you've got multiple steps, multiple discrete variables, that you need something more powerful. But they're a great place to start. So decision trees, some of you might be familiar with these. They're very simple. You just take your experimental point, send it down the tree, and just put it in one of the baskets at the bottom. And the fitting of the decision tree is basically just creating these branches in order to create meaningful baskets at the bottom. They're very good for kind of simple problems. So when you have a simple relationship and you have very little data, a decision tree is going to be a great way to capture that relationship and very quickly start making decisions. Whilst they are very simple, one of the pitfalls with decision trees is that whilst they seem very simple, there are a lot of kind of levers that you can pull. There can be a lot of setup involved with these. A lot of packages which make these trees can ask you kind of like a wealth of questions like how many layers you want, how many branches you want, what the likelihood of a branch split is. If you're quite new to these techniques, it can be difficult to know how to answer some of these questions. But fortunately, we do have a solution for that in AMLearn, and I'll tell you about that in a few slides' time. So next, we have neural networks. So a lot of you might be familiar with these. And the characteristic feature of neural networks are these nodes or neurons. And the way that it works is that we send our input value in. So these inputs correspond to our various variables. And we send them through these various nodes. And as each input passes through a given node, it undergoes a multiplicative calculation, which is the weight, an additive bias, and then it's passed through an activation function. So each input is passed through various nodes, each of which is going to have different weights and different biases, and ultimately reaches the output, which should give us our prediction. So when we're fitting our neural network, we're basically just fitting what these weights should be at each neuron, what the biases should be at each neuron, so that we can accurately correlate our inputs to our outputs. Now, a few years ago, there was a bit of a misconception. And the general conception is true, where often neural networks do need large sums of data to be able to work well. I think a lot of them were developed by these large organizations for things like predicting financial markets, or kind of understanding like kind of global healthcare features, or basically areas where you have very large amounts of data, millions of data points. And through the work that we've been doing at Accelerated Materials and previously at the University of Cambridge, we figured out smart ways to augment these techniques to work with chemical systems where you're going to have much smaller data sets. You're probably going to cover maybe 50 experiments, 100 tops. And we've managed to make these networks be very effective at capturing the complex relationships in kind of multi-step reactions where you've got many discrete variables, and be able to perform well with relatively smaller data sets. So that was surrogate modeling. So in step one, you would pick one of these models, pick the parameters for the model, model your experimental data, and then the next step is to use an acquisition function to determine which is the best experiment that you actually want to physically perform. So I won't go into too much detail about acquisition functions, but one of the benefits of Bayesian optimization is that it's quite amenable to multi-objective optimization. So a key thing to note is that not all Bayesian optimization is multi-objective optimization, but the way in which we do it here, it is multi-objective. And this slide will show you how it works. So in chemical process optimization, it is quite common for us to have objectives which are conflicting with each other. So on the x-axis here, we could have something like yield, which we're trying to increase in this direction here. And we might have something on the y-axis that we're trying to minimize, for instance, cost, which we're trying to minimize here. So our kind of optimal experiment would be in this corner here. And these principles will apply regardless of if you're any combination of maximizing and minimizing and any number of objectives. but 2D is quite easy to visualize. So when we have these conflicting objectives, one way in which to tackle it is through what we call Pareto optimization. So as we're increasing yield, we might have an instance where something else, like our cost or our impurities, might also increase as we're increasing our yield. So there might be situations where we can never get our utopian or ideal solution in the corner here. So in this scenario, what we do is we try to find the optimal trade-off between them. So even though at first glance, it might be easy to say that this experiment here, or perhaps this one or this one is the best one, because it kind of gives you the best compromise between them. But you might have a situation where you're just interested in having the best yield regardless, and you might be willing to take a small compromise in cost in order to get that increase in yield. There might be other processes which are just hell-bent on reducing costs, and as a result of that, you might be willing to compromise yield in order to get that cost. So with Pareto optimization, you don't have to make that decision now. It will just find the optimal trade-off between these two variables, and you can make the decision later. The difference between the blue points and the orange points is that the orange points are optimal, while the blue points are not. So if we take a look at these two experiments here, both of them are a similar yield, but this one is at a much higher cost. So there's no reason why you would take this one over this one. So this is considered suboptimal. It's a similar case here, where this one gives you a similarly high yield, the orange one is at a lower cost, so the blue one is considered suboptimal. And for a lot of these multi-objective Bayesian optimization algorithms, their goal is just to fill in this Pareto curve. So back to the Bayesian optimization loop. So looking at the steps involved in the Bayesian optimization process, well, we're thinking about how it relates to chemistry. These three steps at the top are very easy to automate because they're all purely computational. Fitting a model, selecting the experiments, appending data to a data set. These are all things that we can very easily write scripts to do. Where we can unlock real power in the process is if we automate running the experiment and collecting the result. Because then what that allows us to do is it allows us to give the algorithm full control over the entire process. Once it's kind of modeled the experiment and found an experiment that it wants to run, it can then autonomously run the reaction, collect the data on its own, append the data to the existing set on its own, and decide what it wants to run, again, completely without human intervention. And this is effectively what a self-driving lab is. The system has complete autonomy to both make the decisions and run the reactions itself. So let's take a closer look at self-driving labs. So firstly, in a fully self-driven lab, the whole process is entirely autonomous. So the software has the ability to run reactions, to analyze the results, decide where it wants to go next, and do this whole loop on its own without human intervention. Often, it will be a data-driven approach. So it will likely use Bayesian optimization where it's taking feedback from each reaction to influence the decision that it makes for the next reaction. So because it's autonomous, you can get continuous operation. So it's not going to need sleep, it's not going to eat. And even at the stages that we're using them now, these systems are robust enough to run not only without human intervention, but they can also be run in an unattended manner. So they can run around the clock and drastically reduce the time needed in that way. And then when we couple the automation with the machine learning, which is already reducing the time and cost needed for experimentation, we can really rapidly reduce the time and resources required for chemical process optimization. So to explain it, I'll just dive straight into a case study. So this is a reaction that I've run many times on self-driving lab systems. I think I might have mentioned at the start of the presentation, I've been doing this quite a long time now. I first worked on this system in a self-driving lab application, I think in 2013, and I've run it many times since then. It's quite a nice reaction to run because the reagents are quite low cost. They're usually available in the lab, and it has quite complex reaction pathways through which it can proceed, and it's quite nice for demonstrating the capabilities of this system. So we're reacting benzaldehyde with acetone under base catalysis, and this is the molecule that we want to make here. It's quite a nice system because the reaction will very readily continue to form this guy, this dye product. And the acetone can also react with itself to form mesotile oxide and then further polymerize here to make loads of other products too. And in this case study, we're going to be trying to maximize the yield of this particular material whilst minimizing the cost, the materials cost of this reaction. So the variables that we're going to optimize are the concentrations of our 3 reagents, the temperature of the reaction, and the residence time. So this reaction was done in flow. So this gives you a schematic of what a typical self-driving lab setup can look like. This is the schematic for this particular reaction. As I've mentioned, a lot of self-driving lab systems are continuous processes, but that's not to say that you can't do self-driving labs in batch, particularly with kind of creative use of hot plates, beakers, or more advanced systems like ChemSpeeds. You can absolutely have a self-driving lab with a batch reactor too. But this system is continuous. So we have a pump for each of our reagents. The reagents meet at these T pieces, and then they're heated in this reactor here. Once the reaction is finished, most of our product is collected in a vessel here, but we take a small amount of material and analyze it using this HPLC system here. So the HPLC system is able to not only calculate the yield of our desired product, but the yield of all of our side products, the amount of reactant remaining to calculate conversion. And all of this information is pulled from the resulting HPLC chromatogram. It's sent to the algorithm, which uses this information to decide how it thinks it can improve the reaction. And then a second reaction is run at different concentrations, different temperatures, and a revised time in order to try to increase the yield and reduce the cost. If you're wondering what this thing looks like in real life, this is physically what the system looks like. So our pumps are here, our reactor is here, our reagents are stored here. And once the reaction is finished, we have a couple of valves here, which can send the reaction mixture to either an LC system, a mass spec system. There is an NMR under the bench and a GC system behind it. We also have a robotic liquid handler, which is able to select chemicals for discrete optimization. That's a clue for kind of like the next example, which is coming next. But for this optimization, we can see the results of it here. The system performed 67 experiments without any human intervention. There were 20 blue training experiments and 47 orange optimization experiments. And if we look at the shape of this, where we're trying to maximize the yield, minimize cost, and we want to reach this region here, we can see that the shape of the plot is very similar to kind of like this ideal plot that we had here, where once we've given the system the initial data set, it instantly knows where the optimal experiments are. And rather than having to search, it can just begin to fill up this Pareto front to give you those optimal reaction conditions. So this is an optimal case where our initial design was good enough that the system kind of had a very good idea of where to go. And we only had like a few stray experiments at the start before it could nail down the Pareto front and begin to find those optimal experiments. But that's not to say that if your algorithm doesn't immediately hit these orange points or hit this Pareto front, that you failed. For a lot of complex problems, the algorithm might need 10, 20 experiments in order to smartly search the optimization space in order to get to this level. So it's not just simple reactions that we can do. These tools are a lot more mature now, and they can be applicable to much more complex reactions and complex problems. So in the next few slides, I'll be giving you a more complex example where we've done multi-step optimization with multiple objectives and selection of discrete variables. So this is a pharmaceutical process. I've masked the reagent chemicals, but you can still get a good idea of what the scale of this optimization was. So we basically have, this is a substitution reaction between A and B. to make an intermediate C under base catalysis. We're then taking this intermediate C, reacting it with another molecule D, and this was actually a ring closing reaction under acid catalysis in order to make our final molecule E. This is much more complex than the previous example. We've got 8 continuous variables, all of the concentrations times for each step. We've got 5 reaction solvents, 7 bases for step 1 and 10 acids for step 2. The objectives are the same as the first reaction, where we're trying to maximize the yield of E whilst minimizing the total materials cost. And for this one, there were some really expensive reagents, so it was really critical for us to minimize the cost here. And in the interest of time, I'll jump straight to the results here. So I've actually given you a comparison, which kind of shows how far we've come with Bayesian optimization. So this reaction was actually optimized twice. Firstly, the multi-step reaction was optimized by TSEMO, the algorithm that we developed at Cambridge a few years ago. And this is an example of what happens when the problem is kind of too complex for the surrogate model to accurately understand. So the blue experiments are our training experiments, and the orange experiments are our optimization experiments generated by the algorithm. And you can see that the system is really struggling to get above 5% yield. And the reason for this is that this was quite a challenging problem. So in all of these solvents, acids, and bases, I think only like one of the solvents worked, one of the bases worked, and a couple of the acids worked. And even if you do find that combination, you then have to make sure that all of the continuous variables are in their right ranges in order to get yield. And this was just for step 1. So it was a very challenging reaction to optimize. So we went back to the drawing board and updated the algorithm, and we can see that the performance was much better. Our yields are almost double what we achieved in the previous optimization. And we can see that we have a Pareto front that's much closer to what we had with our previous ideal experiments, where the system knows where the ideal experiments are, and it's just filling in the Pareto front. In order to ensure that there was no bias between these two, you might notice that the training experiments are identical between the two. So they were given the same initial data set, just set to go. And you can see that even with kind of more complex processes, we can have confidence in these tools to find the right results. So if you were doing this optimization manually, and I've been quite generous here by just multiplying the solvents, acids, and bases. I could have done these exponentially, but even with multiplying them, we would have to do 90,000 reactions here to optimize this chemical process. And here on the right, I just did 70 experiments. It was over the course of 1 weekend. I wasn't even in the lab. I think it was Chinese New Year weekend. And the system ran all of these experiments completely autonomously, picked up all of the chemicals, did all of the reactions, collected all of the data. And the other nice thing is that it's not a black box technique where, if I go back a moment, the system does also collect all of your materials here. So you can always go back, reanalyze all of the reaction mixtures. You have a record of what you made, rerun any analyses. So you can have confidence that the data that you did collect is accurate and representative of the process. So I mentioned AMLearn a couple of times, and this is probably a good opportunity for me to kind of more formally introduce you to it. So AMLearn is our easy-to-use, code-free package for automation and machine learning. So it handles both the automation aspect of a self-driving lab and handling all of the Bayesian optimization. From a Bayesian optimization perspective, the algorithm is very powerful. We spent years developing it, both at the University of Cambridge and at Accelerated Materials. And it has all the features that you would expect from a modern Bayesian optimization algorithm. So you can optimize for continuous variables and discrete variables. So you can select things like your solvents, catalysts, acids, bases. And it has support for a range of models, as in all the models that I showed you at the beginning of the presentation. So this means that regardless if you have simple problems or more complex problems, system has the capabilities to be able to handle it. And then the key question is, how do you know which model to use? Well, this is where the algorithm is quite nice, where you don't have to worry about any of that. It is adaptive. Any given stage of the Bayesian optimization cycle, it will look at your data set, look at your problem set, and automatically suggest the best model for you. With respect to the settings for each model, like with a neural network, how many nodes you need, how many layers you need, you don't have to worry about any of that. the algorithm will work behind the scenes to ensure that your model is best set up for your optimization problem. And I haven't mentioned it on this slide, but it is a multi-objective algorithm that uses Pareto optimization. So usually I think you can throw up to about 3 or 4 objectives on it, and it will handle it no problem. So in terms of self-driving labs, we support a range of devices from a range of manufacturers. We start with simple things like syringe pumps, peristaltic pumps, moving on to pieces of analytical equipment, HPLC systems, NMR systems, and extending all the way to kind of fully automated flow chemistry systems. So some of you might have systems from manufacturers like Vaportech or ChemSpeed, which are very competent automated platforms, but it can sometimes be very difficult to kind of close the loop, to add analytical equipment into them and interface them with machine learning technologies. And we're here to basically provide a solution for that without any code, help you get started quickly and easily. We also have our own bespoke hardware that we use to synthesize nanomaterials to give you a very high degree of control over particle size, morphology, crystal phases. And we've used Bayesian optimization quite extensively in helping our clients meet their material needs goals, whether that's reaching a particular particle size or a particular crystal phase, or optimizing the chemical composition of their materials. And yeah, that's pretty much it. So yeah, one variable at a time, and DOE techniques are very valuable, but they can sometimes struggle when it comes to very complex problems. And Bayesian optimization can be very useful in helping you reduce the time and efforts that you need in order to optimize your chemical processes. And when you combine them, these techniques with automation, you can really supercharge your optimization process and really bring down the time and the cost required to optimize these processes. I did throw a last slide in at the end, because I know some people do have some concerns about these techniques. And I do want to assure you guys that it's kind of all about helping to assist you guys rather than completely rewriting the way that you do things. Basically, just reduce the time and the energy to do the more mundane tasks so that you guys can focus on the things that are more important. You guys always have control, so you always set the limits. You decide where it goes and where it doesn't go, and you can stop it at any time. Sometimes it's easy to think that it's just a black box model and you have really no understanding of what's going on in the background. But given that we have uncertainty, we will always have some idea of what the confidence levels are of any prediction that the model is making. And once your model gets more accurate, there are a whole host of insights that you can gain on your data that are powered by machine learning. It can give you very detailed information on the complex relationships between your variables and your outputs, or even your variables and your variables. And yeah, all of those are, of course, included in AMLearn. And finally, I think my last message to you is to kind of like not be afraid of these techniques. I know sometimes when we're in the lab as bench chemists, we can think that these automation and modeling capabilities are probably for people who can code, or people who are able to kind of do automation or electronic engineering. And the key thing to note is that these technologies have matured to the point where you don't need any code and you don't need advanced knowledge of statistics or automation in order to harness the potential of these technologies. You do need domain knowledge on your system. So provided that you understand your system, where to optimize, which variables to give it, you can quickly get started and begin utilizing these techniques. Yeah, so thank you all very much for attending this webinar. I'll be happy to take any questions. I know that some of you might be viewing this after I've presented this. This might be uploaded somewhere. So if any of you have any questions, then do feel free to contact me on this email address, and I'll be happy to answer anything later too. But yeah, thank you very much. Back to you, Zara.
Thank you, Mo. We did have a few questions come in, so we can move swiftly onto those. The first question we have is to clarify, are neural networks and decision a tool within the Bayesian optimization umbrella?
Yes. So you can still hear me okay, yeah? So the key thing to note is that they can be used as tools on their own, and they can be used in relation to a Bayesian optimization workflow. So I had a slide up where I was showing how you can just use predictive modeling on historical data. So if you have historical data on a process, you could, for instance, fit a neural network and model your process, and then just ask it to, or just make predictions until you've got some experimental conditions that you want. And you can do that in the absence of Bayesian optimization. And you can do that also with decision trees. I guess what Bayesian optimization is I guess the acquisition function is the secret sauce here. The acquisition function is what turns the neural network into a Bayesian workflow.
Perfect, thank you. Let's move on to the next question. Can you talk more about the quality and criteria for experimental data to be useful for an AI workflow?
Yeah, this is quite a complex question. Probably do a whole webinar on it. But I think there's a saying in machine learning, quality in, quality out. So I guess the efforts that, as much as you can control and maximize the reproducibility in your experimental conditions, they will be reflected in the model and the model's ability to predict reaction conditions and get you to the optimum faster. If you do have an experimental process that is quite susceptible to noise, there are now models which can kind of separate experimental noise from the model uncertainty, so that your experimental noise is not influenced, or it has less of an impact on your Bayesian optimization capabilities. But yeah, as much as, whatever you can do to increase the reproducibility of your process will be proverbially appreciated by the model.
Perfect, thank you. And how many parameters does AMLearn optimize?
So I would say anything up to about 20 variables. This can be a mixture of continuous and discrete variables. And I would say up to about 3 or 4 objectives. Of those, I would say the objectives is more of a limiting factor, because you will need you basically have an individual model for each of your objectives. And the acquisition function is what combines them. So adding additional objectives then will kind of introduce another arm to that workflow. So if you wanted to go above 20, you probably have more room to do that. Whereas with objectives, I think once you start going to about 5 or 6 objectives, without going to the cloud, it might start to slow down. Even with 3 or 4 objectives, it might take 20 to 30 minutes, maybe an hour if you've got a slow laptop, to get a calculation. You can always add more variables, and it's just a case of how much computation power you have and what your patience is like.
Please, can you define a descriptive and parameter?
Let me just see that in there. One moment, please. Can you repeat that question, please?
Yep, please, can you define a descriptive and parameter?
So by descriptive, it's possibly descriptor. So so a parameter is just something that we want to optimize, and people might be using the terms interchangeably. This is something that we can take feedback on you guys too, particularly if you're users of AMLearn. So yeah, the terms parameter and variable are commonly used quite interchangeably. A descriptor is basically a number that you can use to describe a discrete variable. So if you have something like a solvent, an acid, or a base, there are ways for the machine learning algorithms to kind of understand and process these without you giving them additional information. It will just collect its own information. But a descriptor is information that you can give on these variables that will kind of help the system to understand them quicker. So for instance, if you're doing solvents, for instance, in a liquid-liquid separation, you might have something like polarity, or if they were materials, you might have something like a pKa. And yeah, descriptors are just information that you can give on your discrete variables to help the system.
Yeah, thank you so much, Mo. And I guess in the interest of time, we can sort of wrap up here. But again, yeah, thank you so much for that insightful session. And thanks to everyone else for joining us today. We hope you found the webinar valuable and it gave you a clearer view of how AI and machine learning are shaping the future of R&D, particularly through tools like AMLearn. We did have some great questions come through, but if we didn't manage to answer your question, then please feel free to get in touch, and we'd be more than happy to answer those. A quick reminder, this webinar is part of our ongoing AM Academy series, where we share knowledge and tools to help accelerate materials innovation. And you can explore more webinars, articles, and technical resources at acceleratedmaterials.co/AM Academy. We'll also be sharing this recording on our YouTube channel shortly. So if you want to revisit any parts or share it with colleagues, then please do keep an eye out. Thank you again for spending your time with us. We really appreciate it. Hope everyone has a great day, and we hope to see you at the next AM Academy session.
Yeah, bye everyone. Yeah, please do email me.